Chemistry is the study of matter and energy and the changes between them. So the previous lecture we talked about matter. So now let's talk about energy. So energy is the ability to do work or produce change. And in chemistry, it's all about bonds. Energy is stored in bonds, or energy is used in bond formation or bond breaking. Whenever we talk about bonds and energy, we need to remember that anytime we need to break a bond, we're going to have to put energy into breaking it. Systems tend towards their lowest energy configuration, and chemicals want to be bound together. They are more stable that way. And if we want to break them apart, that's going to require us to put energy in. Putting energy into a reaction, into a system, is called being endothermic. Energy goes in, in. When bonds form, they give off energy. This is exothermic, the release of heat. Energy is exiting the system where the bonds are being formed. So if I'm heating water up to turn it from water into steam, I'm putting energy into that water to break the attractions between the water molecules to cause them to become steam. If that steam were to cool down, it would release energy, exothermic, and become liquid again. So hydrogen and oxygen, when they react, they combust, they go boom, cause an explosion that releases energy because a bond is being formed. If I want to break the bond between hydrogen and oxygen, if I want to break water apart into hydrogen atoms and and oxygen atoms, I would have to put energy into the system via electrolysis. I'd have to pass an electrical current through them. So that would be an endothermic reaction. To break a bond, I'm going to have to put energy in. Now, energy, just like mass, has to be conserved. You can't create energy and you can't destroy it. So energy can only go between being energy of motion, meaning I'm running forward, I'm running backwards, or potential energy, energy that is being stored up. So in class, I take my keys and I raise them above my head. I've increased their potential energy. They've stored energy in the keys. When I drop them, as they fall down to the ground, that's kinetic energy. In chemistry, kinetic energy is felt as temperature. You are cold or you are hot because the air molecules around you are bombarding you with a particular amount of energy, a particular amount of force. And that's what you feel as energy in chemistry, is the temperature. Temperature and kinetic energy are directly related. Potential energy in chemistry is all about bonds. What type of bonds you have and how they can be broken or how they are formed. Now, some words I've been using in this lecture that you might want to know. The system, whenever you're in chemistry and you talk about the system, you're not talking about fighting the man or some political game. You're actually talking about where a reaction is taking place. So in this picture, the system is this circle. Everything is happening inside of that circle. And from the edge of that circle to the end of the universe is the surroundings. So if the system absorbs energy, it's going to absorb it from the surroundings. If it releases energy, it's releasing it into the surroundings. Now, when a system undergoes a phase change and you're dealing with a pure substance, that pure substance actually does not change temperatures during that phase change. So if you take a pot of water and you put it on your stove and you boil it, and you take the temperature of that boiling pot of water, it will be at exactly 100 degrees Celsius from the minute it starts boiling to the last possible drop of water evaporates. It will not increase in temperature at all. And this is because you need to supply all of the energy to break all of the attractive forces in order to complete the phase change before you can continue to heat up the substance. So you have to supply all the potential energy that you'll need before you can continue to supply kinetic energy, i.e. heating the substance up. Pure substances gain energy at a very set rate. This rate is called their specific heat. It's the amount of energy it takes to increase the temperature of something by 1 Kelvin if you have 1 gram. So I kind of stumbled over that. Specific heat is the amount of energy it takes to raise 1 gram of a substance 1 degree Celsius, or 1 Kelvin. And it's symbolized by the letter C. If we were to graph the amount of energy we put into a system versus its temperature, going all the way from a solid all the way up to a gas, it would look like this. Where as we are heating the solid up, we're increasing its temperature. Once we reach the melting point, the system undergoes fusion, which is another fancy word for melting. As it melts, it stays at the same temperature because we are adding potential energy at this point. We were adding kinetic energy before, but this is a different form of energy, and therefore there is no change in temperature. Once every single drop of, or every single part of the solid melts, we have a liquid, and we can continue to add kinetic energy. When we reach the boiling point, the substance begins to evaporate or vaporize, turning into a gas. We're adding potential energy again. When every single drop of the liquid has vaporized, we can add kinetic energy to the gas and increase its temperature. You can calculate how much energy you have for each section of this graph if you know a couple things. The formula to do so is Q equals mc delta T for any sloped region, because when you have a sloped region, you have a change in temperature. That's kinetic energy. You can calculate the kinetic energy if you know the mass, which is m, the specific heat of that substance at that phase. So if you're dealing with a solid, it would be the specific heat of the solid. If you're dealing with a liquid, it would be the specific heat of a liquid. They are different for different phases. And delta T is the change in temperature. It's the final temperature minus the initial temperature. If you're dealing with the flat section of the graph, a flat section has no change in temperature, and therefore we cannot use Q equals mc delta T because we have a different form of energy. This is the potential energy. So the formula for that is simply the mass times the heat of, and then whatever phase change you're dealing with. So if I'm dealing with fusion, I would use the heat of fusion, which is a value you'd have to be given or would have had to calculate from a previous problem. If you're dealing with vaporization, you're going from a liquid to a gas, you would use the heat of vaporization. But let's say you're cooling something off, because the graph also works going backwards. You would use the heat of condensation if you're going from a gas to a liquid, which is just the negative value of the heat of vaporization, because you have to give off the same amount of energy that you took in to undergo a phase change. So for the sloped regions where we're adding kinetic energy, Q equals mc delta T, where C is the specific heat of, in this case, ice. On the flat regions, the plateau, where we're undergoing a phase change, in this case this would be Q equals m times the mass times the heat of fusion. We have another sloped region. This time we're heating up a liquid, so this would be the mass times the specific heat of liquid water times the change in temperature, which, and since this is water, I know this is 100 minus 0, so it's a 100-degree increase, so Q is positive. If we were going backwards, Q would be negative. Another flat region, Q equals the mass times the heat of, in this case, vaporization. And then lastly, Q equals mc delta T for this final sloped region, where C, we would use the specific heat of steam. Now you have a basic understanding of energy when it comes to chemistry.